and we've done SSA as kind of one of the main things we did in NIT. And it simplifies the data flow graph, but it also has a whole bunch of advantages, like making it easier. It can look at various sections easier and making code much easier. So now we're going to talk about control dependencies. So control dependencies are they're different. They're different and a lot harder to kind of wrap your head around. So, so this is the definition of control dependency. So we're going to do this very, very slowly because it's not simple to understand what's going on here, but there's an intuition. So first of all, do people have an a priori notion of what control dependency means, or control dependency? The intuition about control dependency is that basically some instruction is going to be control dependent on another. So A is going to be control dependent on B if B kind of affects whether or not A executes. Right? So if B affects whether or not A executes, then A is control dependent on B. Right? So B kind of is the thing that affects execution of A. So A is control, it depends on B. Okay? So let's take a look at what this definition is. So basically, the idea here is that we have, let's say, a node in the control flow graph, Y. It's going to be control dependent on another node X if and only if X determines whether Y executes. And the idea here is that we're going to have a graph-based definition of how we set that up. So first, there has to be a path from X to Y. So there has to be a path from X to Y. So there's a path from X to Y, such that every node in the path other than X and Y, so all these nodes in here, have to be post-dominated by Y. Okay, what does post-dominated mean? Does anybody know post-domination? What about domination? Oh, you know what post-domination means?
Yeah.
What does it mean? Where do you know that from?
I took another class, and there's some material I read.
Really?
Yeah.
Wow, cool. It's a general graph theory kind of idea. But anyway, so what does post-domination mean?
So basically, all the paths goes from X to the axis must go through Y. Then Y post-dominates X.
Okay, wait. Yes, that's right. Let me say that again. So, say we're at X, okay? And every path from X to the end of this procedure has to pass through Y. So if we want to get to the exit, we have to pass through Y. Then we say that Y is post-dominated by X. Okay? Does that make sense? So when Y, it's Y, so when we say Y, X is post-dominated by Y. So when we say that X is post-dominated by Y, what we really mean is Y has to happen. There's no way to avoid Y. There will be Y. Right? It's like, that's what it means well, actually, that's not entirely true. That's not entirely true. There is one way, when we say that X is post-dominated by Y, there is one way that you can never reach Y. What is that?
Terminal?
Huh?
Exception or something?
No, actually, exception you have to encode it with control flow. So what's the other way? So if you reach the end, you've got to pass by Y. Yeah, so you may have an infinite loop in here, you'll never reach Y. But the point is that if you are to reach the end of the procedure, you have to pass by Y. Now, that's the general definition of post-domination. What we're saying here is something different. We're saying that every node other than X and Y is post-dominated by Y, which means that if we're in here, any node in here has to be post-dominated by Y. It means that if we're in this portion of the control flow graph, there will be Y. You got it. Y is inevitable, right?
You're saying X here is like a if check.
Well, yes, that's
If you take
exactly.
true.
Well, actually, I'm not saying that yet. I'm not saying that.
As an example.
Yes, I mean, the X will eventually, yes, but we'll see what, but let's just get to the definition. So, so basically the definition says that so Y depends on X, it's control dependent on X. If there's a path from X to Y, and every node other than X and Y is post-dominated by Y. And X is not post-dominated by Y.
Mm.
So if X is not post-dominated by Y, what does that mean?
You may not take that path.
Exactly. There must be another path that can reach the end without passing through Y. There must be another path that doesn't go through Y, because if all paths went through Y, then X would be post-dominated by Y. Right? So what that really tells us is there must be another path that circumvents Y and reaches the end.
Mm-hmm.
So in other words, what we're saying is there's a path between X and Y, and everywhere inside here, you're forced to execute Y. But this is the first node, if you kind of distance yourself from Y, that really affects whether or not there will be Y, right? Because as soon as you make this choice, if you go down this path here, as soon as you make that choice, and you go to the next node in this path, there will be Y. You're stuck. You're stuck on the Y path, right? There has to be a Y. Yes?
So this is assuming there's only ever, or is this implying that Y can only possibly have one control dependent, basically? Like, is it possible that it could also have Z going into Y?
Yeah, there could be there could be many branches. So I mean, we'll see later. But I mean, yeah, you can have Y can be control dependent on a variety of things, not just one thing. Yeah, sure. Yeah.
Are we assuming like a unique terminator node here?
Yes.
Okay.
Let's just, for simplicity, yes. Let's assume, and if there is no such terminator node, then we could just create a new one and have all your. If you have, for example, return statements, you could just create one thing at the end and have all the returns kind of go to that thing.
Okay.
So, yeah. So, so this is a mathematical definition. So how does this actually, so does this make sense?
Mm-hmm.
What this mathematical definition is trying to encode? It's trying to encode the fact that there is a path between X and Y, and as soon as you go down the first element in this path, you're forced to go down through Y. But if you're at X, you still have a choice. You haven't committed yet to go down the Y. But when you make this choice, if you go down just one node path in this path, then you're stuck along the Y path. So basically, what this is, as you're mentioning, this X ends up being a branch that decides whether or not you're going to go down the path of Y or not.
But it's not necessarily, if you take the other path, it's not necessarily excluding you from going to Y, right? Like you could still wind up in Y, like maybe.
Yeah, so there are weird cases where you can have bizarre control flow. What ends up really happening is the more common situation is that you have an if then else, and this is one side of the if, and that's the other side of the if.
Yeah.
But you're right that if you have bizarre control flow where you have, two sides of an if, but then one side can kind of jump in on the other side, and then, right, I mean, on a particular, you can create control flow like that with go-to statements. But that's kind of, that's yeah.
Okay.
Okay. So that is, okay, so let's take a look at this piece of code. So if we look at this code, what are the control dependencies?
7 is control.
So 7 is control dependent on what?
6.
7 is control dependent on 6.
And then 3 and 4 don't co-depend on 2.
So 3, 4, control, oops, not CPU, it's CPU. Control dependent on 2. What about, okay, 5. Is 5 control dependent, so wait, sorry. Is 7 control dependent on 5?
No.
No, because 5 is not the decider, right? Remember, what you have to have is you have to have something where you have to have this thing where,
Branch.
right, and actually, when you end up having, the reason why it's not is because 6, basically every path, see, 6 is not post-dominated by 7. You have to have every path along that's right after this node be post-dominated by 7. And so here, there's, it's not. But if there was another statement inside here, then all of these statements would be control dependent on 6. Now, okay, what about, so that's not, what about, so now you'll notice how, okay, so that's basically, that's pretty much it. Now, the other thing is the way we usually encode this also is that we start off with, there's kind of this, you can think of it as the procedure entry node or the procedure node that represents kind of the decision as to whether to make this call versus not make this call, right? Because at some point someone's got to call this procedure for us to enter. So, for example, this 1, you can imagine as this node 1 is control dependent on this procedure, on this kind of node that represents whether or not you enter the procedure or not, right? So in some sense,
could we say that everything 1 to 8 is control dependent by that procedure? Because the path to any of them?
that's right. That's right. They're all going to be control dependent on this one thing. So all of those, yeah, that's exactly right. Now, what you can do is that you can actually, if you look at this relationship, basically now this becomes a what is it called? A relationship between nodes, a relation between nodes. You can actually, so it turns out that this relation is in some sense nested. And you can actually represent it as a tree, and you can create basically what are called control dependence regions. So in particular, you have the procedure kind of node, and 1, 2, 5, and 6, and 8 are all control dependent on, directly control dependent, right? The closest control dependence that they have are directly control dependent on proc. Now, other things like, for example, 3 and 4 are also dependent on proc, but they're also dependent on 2. So basically, you kind of put them underneath 2. And you kind of can label the things as to which side of the branch it is the true side or the false side. Okay? So, okay. So this thing here is called a control dependence graph. Okay? And it's an alternate way of representing the control of your program. Okay? Now, this is fantastic. We are now on the path towards a very fancy, advanced, really cool representation of control dependencies and control flow. So I am now tempted to, I'm not tempted, I will delete this control flow graph. Let's just throw this away. We have all of our statements represented there. Is that okay? Why not?
From 3 to 4, how do you get to 5, for example? You have to have some kind of ordering.
Right, so if we assume that these nodes here are ordered, let's assume that basically the children here are ordered, then we keep the ordering of the actual statements in each control dependence region, right? So these things are called a control dependence region, right? So this entire thing is one region, okay? And if we keep the order, then we actually maybe are doing okay. We're kind of preserving a lot of what's in the program. Now, the truth is, what we want to do, yeah.
How do you, so in our graph here, we'd actually have guards on these.
Yeah, so you have to store the guards somewhere too. That's the other thing you have to. So the guards are actually, so in some sense, when you have this node number 2, I mean, really what it is that the nodes that have multiple children in this graph are branch nodes, which basically will have a branch condition.
Well, I mean, I look at proc and that doesn't have it. It's not branch.
Yeah, because that's just, right, so proc is true.
I mean, so on
The
a
condition on proc is true. I mean, you kind of are assuming that you're entering the
I
thing.
guess I'm wondering, on a larger, so other than the entry, you never have more than 2. Is that what you're saying?
Well, yeah, it's a little bit confusing. It depends on how you represent things. So there's actually a lot of choice and there's a lot of variation. But if you have, for example, the question is, suppose you have 5 statements here and 5 statements here. What would you do? Right. So one way to do it is to have a whole bunch of all these children be right here, right? But then you have to kind of separate them into true sides and a false side, and also keep the ordering of them. Another way to do it is which is actually the way I'll show it on the next slide, is that you can create a region node for the true side and a region node for the false side, and then have them stored in there. But certainly, if we do that and we keep the ordering all the same, then we can throw away the control flow graph. But the thing is, actually, the whole point of doing this is that we want some flexibility. So in particular, one of the things that's actually really cool is that if you kind of if you look at, for example, in terms of the control flow graph forces you to order statements inside of a control region. So for example, we have this statement, this statement, this statement, this statement, this statement, and it forces us to pick an order of these statements. Here, it'd be great if somehow we basically allow flexibility so that the children of this thing are kind of all reorderable, right? It's all there's no control flow constraints amongst them, and it will also another thing to notice about this graph is that if you want to move a node from one place to another, or you want to move a whole conditional from one place to another, really all it is basically like reordering these two. Like this will swap the order of this entire conditional, it'll move this entire conditional to a different place. So code motion looks very different in this kind of graph. You can actually do really large code motions by doing very, very simple graph transformations. But the point here that I'm trying to make is that what we're trying to get at with this control dependence relation and this control dependence graph is that we don't want to impose this strict ordering that we have in the control flow graph. But if we don't order things here, then there is a problem, right? Because we're not going to remember which order things go. But what we can do is so actually what's really the constraints that we have to make sure are valid, right? So can we reorder some of these things?
Yeah.
Yeah, some of them we can. And so what is the key thing that we want to make sure we don't violate? Huh?
Your depth use.
Yeah. You want to make sure you don't violate depth use chains. Right? So actually that's fundamentally, so you want to make sure you don't violate, you don't reorder things in your data flow graph. And so what you can do is, if you add a data flow graph on top of this representation, then that's something that is called, I'm going to skip here, it's called a program dependence graph. And so here's what it looks like here. These are this is the data flow graph for this example. And this is kind of this exact same tree, except that I added these regions here, these kind of nodes so I can hang more stuff onto the true region and the false region. And once you superimpose the data flow graph on top of this on top of the control dependence graph, so control dependence graph plus data flow graph, you get something called the program dependence graph. And that's a complete representation. You can delete your program, your control flow graph, and you just keep this representation, which is the control dependence graph plus the data flow graph. And now, in some sense, everything is kind of fluid. It's kind of, you don't have these things ordered anymore. It's kind of, they're all, you can imagine, I mean, at some level, that they're all just floating around. And really, the only constraints are the constraints imposed by these blue edges. And the blue edges really means that, in some sense, you always want the blue edges to go from right to left, in some sense. So, for example, what are things that you can actually kind of reorder here?
5 can go from 2.
So 5, yeah. So this 5 node can actually go. So you can actually make this 5 node go here, and that would be fun. And notice what this means, right? What is 5 node going? So it really means that you're taking this statement here and pushing it all the way up here. notice how in a control flow graph, this looks like a massive motion, right? It's like, oh my gosh, I'm like traveling through this deep ocean of conditionals. I'm like going off and jumping off this, right here, it's literally just a simple, in fact, you don't even have to reorder it. You just let the whole thing just float around in this representation. Now, what's another example? So this, what?
Region 1.
What about 6?
I was just saying region 1 and 3 are the same, because 2 and 6 are the same.
But 6 can actually go, can't 2 go all the
2
way?
and 6 are the same thing.
What?
I mean,
Oh yeah, I understand, no, but the point is that inside of this root node, can they get reordered? So 6 can't get reordered because it actually depends on,
it can.
oh yeah, it can. So in fact, 2 can go all the way down here, right? Isn't it? Yeah.
Yeah.
So, in fact, what happens with this is that in the representation itself, the point is you're not even, this representation does not even constrain who goes first. That's the point. It doesn't tell you whether 2 should come, in terms of control flow dependency, whether 2 should go after 1 or 5 should go after 1. It just tells you that 5 is in this control dependence region, and 5 depends on 1 from a data flow perspective. And so whenever you serialize your program, whenever you actually generate code for this, you better run 1 before 5. But other than that, it doesn't put additional constraints on you. Now, does that make sense? Did you see what's going on here? Yeah.
So I just want to check. So you could, if you track from 8, 7, 5 to 1, you can cross that path with 8, 4, and 1.
Wait a minute.
How does it work?
8, 7, 5, 1.
Yeah.
So that's just showing the data dependencies.
So I can move to with 5 because
I can basically put 2, this shows me that I can run 5 first, and then I can run 2 and all of its branches, because I would not violate any data dependencies. I would not break any data
So
dependencies.
there's no path going through I and 2, is that one?
Yeah, I mean, for example, if 5 depended on 2, then I wouldn't be able to do that.
Okay, and anything lower than that, like the 4 and the 3 having dependence on 8, it doesn't matter that those...
Well, yeah, I mean, so basically what it means is that, if 8 can't be placed before, I can't move 8 all the way before 2, because 8 requires 3 and 4.
Right.
So if I tried to put 8 before 2, then it would violate this dependency, this data dependency. That basically 3 and 4 need to go before 8.
So the different tracks don't have any constraints with respect to each other.
What do you mean different tracks?
So like the parallel trace from 8 through 5 and 1 doesn't constrain the trace through 8, 4, and 1.
Well, they're all, I mean, they do, you can think of them as just, those are constraints. That means, basically all it means is that 7 needs to run before 8 whenever you actually generate back a control flow graph. The point is, what we've done here is, we've taken this, and we've kind of removed some of the constraints. Like, in this program, in this CFG, when you add the data flow graph to it, you are still forcing, for example, 5 to go after 2, because that's how the control flow graph is encoded. In this representation, it doesn't say that 5 should go before 2. You can think of these as being unordered elements of this root node, and they can just float around in whichever way you want them to. And later on, you can actually generate an actual program from it, because obviously you can't execute this directly. You have to generate a particular sequencing to run on a computer. But the point is that this path here of data flow and this path here, those are just constraints that basically say that 1 should run before 4 and 4 should run before 8.
Right, so like because 5 and 4 haven't reached a common node, you can swap them.
Exactly.
Okay.
Exactly. And the other thing to notice is that if I want to do code motion from inside of a loop to outside of a loop, all you need to do in this case is basically redirect an edge from, let's say I have this, this node, if I want to move it outside of the loop, I just redirect this edge to point to the root node, and that's what code motion is represented as. Right? Moving this thing outside of this conditional is basically represented by redirecting this parent node. The parent of 4 becomes the root. That's what code motion looks like, which is very different than the way it looks like in a control flow graph. Yeah.
I was going to say, when we had loops, we had the concept, because it's not SSA.
Let me not get, okay, we'll get to loops in a second.
There.
Yeah, we haven't done the loops yet.
You just brought up loops.
What?
Because you just said loops, so it triggered it. Never mind.
Yeah, loops are very confusing. This whole representation is actually very confusing.
Yeah, because you could,
Yes.
So with the dependencies, when I generate code, I don't have to satisfy just one of those dependencies. I must satisfy all of them, right?
Right.
Okay.
Right. So all the blue dependencies, you have to satisfy all the blue dependencies, and also the red dependencies in the sense that the red dependencies are control dependencies, meaning that all of these will kind of be all in the same control dependence region. So you have to somehow, basically they're all going to be under the same conditional, you can think of it. And also, all these nodes here that hang off here, there's only one here, but basically all these nodes have to hang under the true side of this conditional. And all of these nodes that hang here have to hang on the false side of this conditional. But the ordering here is not given. And in that, the ordering, you can pick whatever ordering you want based on the data flow dependency.
But I do have to examine, like if I'm in the same control dependence region, I do have to examine like the children of everyone there to make sure that,
Yes. Yes, absolutely. You do have to look at the blue edges for the children as well. Because if you move something whose child node has a dependency that you violate, then absolutely.
So we could like generate the set of allowable ordering from say the root to the 1, 2, 5, 6 by searching everyone's children node and say,
Sure.
This pair of nodes can you swap, this one can you swap, by doing like a transitive closure operation.
Sure. So you can do that. And really, another way to think about it is that and another thing to think about it is that basically what happens is, once you go into this kind of representation, the way to think about it is that it's not like you're swapping these anymore. Now these are unordered children. So you now work with a representation where the children are unordered. And it's a bag of children. And the only ordering is imposed by the data flow constraint. And then you can kind of transform your program in whichever way you want. You can move things around, transform move things by moving, for example, this statement up to here by adding, for example, let's say you want to move this to the root node. All you need to do is make this a child of this, and you let the data flow dependencies take care of the rest of how it's going to be eventually, scheduled. And then what happens is that's how you think about it in terms of your representation, but then of course, at some point you have to convert back to a serializable kind of something that actually runs on a processor. And at that point, what you have to do is convert this kind of mech back into a control flow graph. Turns out that that's actually not easy at all. It's very complicated because it ends up being this very complex scheduling thing where you need to kind of figure out how exactly you're going to schedule these instructions. And it gets complicated, especially in the face of loops. We haven't even gone to loops yet, but loops get a little bit more complicated. But what I'm trying to get at here is that the control flow graph, I'll get to you in a second, the control flow graph is overly specified. It chooses orderings of instructions for you, and it constrains the order of instructions, whereas the idea here is to not overly constrain the order of instructions, right? The whole point of the idea is that this node should be on the false side of this node, but we don't want to constrain it any more than that. We want to let the data flow dependencies kind of determine how it should actually get its data. Yes?
I don't see it in this example, but because I don't think the 4 can go up to the root. In this case, it's on the false string. But are there cases where that?
No, you can put the 4 on. If it's an SSA, you can.
Okay.
Right. If it's an SSA, you can. And now, of course, you're right. In this case, you can. But what?
Why can't you?
Well, actually.
In this case, you could. Because 3 and 4.
Oh wait, because you're modifying A. The problem is the dependency. you're gonna modify
I
A.
mean, if you bump that up, then if you took the 3 side,
Sure, but that's a fluke, right? I mean, in general, because, yeah, I mean, in this case you could, but the point is that in general, it's not like you could just, so, it doesn't mean that, first of all, it doesn't mean that, this representation doesn't mean that you can just move code around wherever you want without checking the constraints. Of course, you still have to do your analysis to make sure that things are safe to move. So when you move something from one region to another, you have to make sure you're not doing something weird.
But we can take things lower in the tree and put it higher, because it looks like in the example, we can.
But you can or cannot.
No, we can, if everything works out.
Yeah, I mean, it's basically, if you could, for example, if you can show that, and especially if this were an SSA, actually, you'd be able to do it as well.
Like if 8 isn't aligned to 4, then we can move 4.
So here's what happens, if you add SSA to this, you would actually get phi nodes, and the way that it works, there's actually an example later in the slides with this. The phi nodes, it turns out that you kind of have to pin them down. You can't, moving phi nodes is actually hard. That's hard. But once the phi nodes are pinned, everything else can kind of flow around wherever. And at that point, you can literally take any instruction and move it to any other control dependence region, because as long as it's higher up, I mean, you have to be careful not to put it lower down because then it's too constraining. But you can move them higher up in a very easy way depending on where you want them to be. And yeah, so sometimes it's almost like you're letting things now float around, and you don't even have to worry about any of these things until you schedule back into a control flow, back to a control flow down.
If we set the finance, you can almost make this like with no if statement. Is what it sounds like. Because if it's SSA and it's finance, then you can almost remove some if statements.
Well, you still need the if statements to basically decide the values of the phi nodes.
Okay.
You still need it. So you still need the if statements, because what happens is when you go back to converting your phi nodes back to a normal instruction stream, you need to decide where does the phi node, which side did you go in. Now, it turns out that actually there's another really cool way to do it, which is that you basically this thing called gated phi nodes. So phi nodes are hard to move because what you have to do is, once you convert back to a CFG, you need to basically kind of keep them in place so you can get the right, the correct things on the two branches, right? You need to get the values of the two things. But there's this thing called gated phi nodes, which basically is very similar to the question mark operator in C. It's basically a 3-operator thing. It takes a condition, a true value, and a false value. Once you do it that way, then your gated phi nodes can also move wherever you want. And now you've got this weird representation, which basically, well, it's not weird, but it's kind of really kind of everything is just flowing in this, or it's kind of floating around in this kind of way where you have the control dependencies, you have the data flow dependencies, and nothing else. You don't have a control flow graph. Everything is just kind of amorphously kind of moving around. And of course, you can do all kinds of crazy stuff there, but then the place where things really get messy is when you convert back to a CFG. That's actually really, really hard.
Sorry, why is it hard to convert back? I just don't get that.
So there's a variety of reasons why it's hard. One of the reasons why it's hard is because nobody really, those algorithms are not very well explained anywhere. And it's also hard because this doesn't even account for loops. So if you look at loops, the representation gets even more complicated. So actually, the original paper on control dependence graphs didn't even have many loops in our examples. So even there's a lot of kind of complexity in figuring out what loops look like in this kind of representation. And once you do that, it turns out it's actually non-trivial to kind of figure out how you actually convert back to because now you have all these kind of nodes, and you have to figure out how they can actually be generated. It's actually not, I'm just saying, there's very little explanation of how it works. We've actually done work in this area where we've actually built representations that are even more flexible than this, and the conversion back is very, very complicated. In part because nobody had done that kind of stuff before.
Is that because you just can't easily represent a loop in this type of dependence?
Well, so, basically there's it's a weird thing. I mean, if you look at, for example, so let's take a look at this example. So what is this going to look like? So, right, what is the control flow, the control dependence graph for this? So, a lot of a lot, I mean, if you can go back to the definition of what it actually, of control dependence to kind of figure this out. But it turns out that it actually is confusing because it has to do with whether or not post-domination is reflexive. So does X post-dominate itself, and that's actually kind of a confusing thing. If you assume that X does not post-dominate itself, then you actually get this kind of loop structure where you have this region. So B1 and B7 are part of the same top-level region. Then you have B1, which basically has a true side and a false side. And on the true side, it's just B2, and on the false side, you have B3, and B4 is this kind of loop node that has, you know, B6 and B5 underneath it. So it's actually kind of a actually, wait a minute. I don't think that's right. I think B5 may actually be at the same level as B3.
Sorry, what does all mean?
Region? So it's just a control dependence region. So one question, for example, here is like, is B5 in the same control dependence region? Is it under the loop, or is it under the same control dependence region as B3? And the point is, you can actually go and do the kind of follow the definition on this and try to do it. There's very few compilers that use this kind of representation because of how complicated it is. It turns out it gets very, I mean, just this fundamental thing of what is B5? Is B5 under the same control dependence region as B3? Like B3, B4, and B5 are all in parallel because they all execute. You know, it's like or is this B5 under B4? Right?
You should be saying this before.
What?
You should be saying this before.
Right, but on the other hand, that B4, on the other hand, yeah, right, but it should be, right, but on the other hand, this B4 has a branch which either goes to B6, right? Right, it's like, this B4 has a branch, and either you do B5 or B6. So before, if you didn't have this loop, for example, like you would basically say that B5 is control dependent on B4, right? So that's why it actually gets subtle when you actually get to the details of how this works in general and making it work in a realistic compiler. We've actually done work that doesn't use this kind of representation. It actually goes the other way, which is to represent everything as a data flow graph. But those things are also, you get into similar kinds of issues where it gets really hard to revert back to CFG. Yeah.
I just thought it might be easier if you just create two graphs and you don't have B6 in one and you don't have B5 in the other. That makes it much easier.
Well, you want one graph at the end to represent your entire program, right? Huh? I mean, you could, but that makes it even more complicated. Okay? Very few compilers use this kind of representation. There's research compilers that have tried doing this, and it turns out that in practice, it turns out to be very tricky and very complicated. In part because it's not an intuitive representation. It's not as intuitive as, for example, SSA. SSA is just a slight tweak on your control flow graph. It's much simpler to understand. It's much simpler to revert back. This is actually much, much more complicated, and there's no, I mean, it's actually not, these kinds of things are not used in practice. So, here's another example. You guys can look at this later. I mean, this is an example where you basically have binodes inside there, and you kind of draw the whole thing up, and it's actually, when you actually, I mean, it's really cool how you can have basically represent this, and kind of everything gets, you can move, once you get to SSA, basically everything can move anywhere. Because you're literally completely free to move any statement wherever you want. They're just in a cloud. The only things that need to be pinned down are the binodes. So you pin the binodes down to the places where they're supposed to stay, and then everything else kind of floats around, and they need to, they're just attacked based on their data dependencies and their control dependencies. And you can, if you guys want, you can look at this example later. Yeah.
On the previous slide, I don't really understand why you were saying that B5 and B3 could be in the same control dependency.
Why could they, right, so, because, why they would be or would not be?
Would be.
Why they would be in the same range, right? Because it looks like there's this branch. So okay. So the reason is that really this B5, it's like, when you think about the structure, the AXC structure, right? You basically decide to go down this path. And once you're in this path, there's this node, which causes some looping, and then this node. Right? So this is kind of the path that you're going to get. Let me put it this way. If you decided to go down here, and you assume that you will reach the end of the program, let's just assume that this doesn't go anything new, then you have to execute B5, right? So that's kind of the intuition why it would be part of, right? Because if you went down this path, then B3 is inevitable, B4 is inevitable, and B5 is inevitable too if you're going to reach the end of the program, right? So that's why if you actually look at the strict definition, but on the other hand, right, that's why if you look at the strict definition, I think B5 would be in the same region as B3 and B4. But on the other hand, you do have this branching structure here, so it's like, wait, but then B5 should, so it actually kind of gets confusing.
So is it like flexible where you put B5?
Well, at the end of the day, all these representations are flexible. You just need to be consistent in your interpretation of how you represent things and how you kind of convert back, right? I mean, really, that's what matters, is that you're kind of consistent. I mean, the point is, all these representations, there's variations on them, right? I mean, nobody kind of takes a representation and literally implements exactly that thing. There's variations, and within a variation you get in a compiler, you just have to be consistent and make sure you get everything right. So,
for example, you could have an edge from B3 to B5 to represent that. They are in the same region.
well, yeah, so you can, or you can just have B5 be part of, I mean, the other way to do it is to have B5 be just part of, you know, B3, you just have them all be here in parallel. Or you can have something where, yeah, I mean, basically you can have multiple edges where this thing kind of belongs to two things. It's dependent both on this and on that, right? That it really, it depends on this thing up here, but it also depends on which direction you go when you do this loop. The thing that's weird about this thing is that even if you decide to go down this path, if you are going to go to the end of the program, you still have to pass through B5, right? That's the reasoning why it would be part of this region up here.
One more question.
Yeah.
Instead of converting it back to CFG may be a big issue. So a nice approach would be go for topological sort. Why wouldn't that work?
Well, topological sort would just linearize everything. I mean, you need to replicate conditionals and branches, and you need to get like this structure back, right? So this kind of like control. I mean, you want to get a control flow graph back, not just a linearization. I mean, you want to get a control flow graph that keeps track of all the branches and how everything is nested, etc. Right? And that's so you can, by doing a topological sort, you will get something that satisfies your data dependencies. But what you need to also encode is this whole kind of control program dependence graph. Sorry, the control part of the dependence graph.
Okay, moving on.
Certainly, I'll tell you this: the original paper that actually described this didn't describe how to convert it back. So, I mean, it's like you're on your own, right? I mean, it's like you got to figure out your own technique. And I know that when I was working, there was a compiler I was working on that was using this representation, and converting back ended up being painful, very, very painful. I mean, I didn't do the conversion back, some other people were doing it, but it turns out that it was not, there were like tricky issues in how to convert. Certainly much, much more complicated than SSA conversion back. Like SSA is like trivial. It's very, very simple. So All right. Any questions? Any more questions? So what's the summary of control dependencies? Control dependencies are less intuitive than data dependencies. They're more complex to represent. They are not often represented in fancy ways. In most compilers, you just have a control flow graph. Most compilers don't use these more advanced techniques. And that's, that's kind of the summary. But I think it's important to get a flavor for what an alternate representation of control dependencies looks like. Because control flow graphs are not the only way to do it. There are other ways. Okay. Cool. So let me. So let's see what's this. So that basically finishes off our advanced representations, the program representations. So now we've done pretty much everything except one thing, which is dealing with procedures. And that's the next part that we're going to talk about. And that's the last segment of the class. Right? Because we have only 2 more weeks left. Right? So 4 more lectures after this. So we're getting close to the finish line. So that's representation. Let's talk about procedures. Whoa. Wait, how do I get out of here? Uh-oh. Okay, this is not funny. Can we do this? Okay. So, function calls are problematic for 2 reasons. First one is that there's actually a cost overhead to actually literally doing the function call. When you do a call, there's a call and a return. You set up stack frames, you have to kill the stack frame. That causes runtime overhead. But the other thing is that there's also an indirect cost, which is that functions and procedure calls prevent you from doing certain optimizations, or they make it harder for you to see optimizations, opportunities for optimization. So there's kind of these 2 costs to procedure calls. So the first thing that you can try to do is to get rid of technique calls to begin with. So basically use things like inlining and other techniques to just get rid of calls to begin with. And if we can do that, great. And for the ones that we can't get rid of, then we're going to basically talk about interprocedural analysis. So inlining is very simple. You guys have heard what inlining is before, right? You take a function call and you replace a call with the body of that thing that's being called. And parameter passing and the returning of the results become assignments. And when you do copy propagations, that's going to eliminate those assignments and those copies. You have to manage variable scoping correctly, but it's usually not that hard. So if you want to do inlining, and if you want to do a lot of these kind of optimizations across procedures and doing analysis from across procedures, you want to use a representation that's called a call graph. So a call graph, every node in the call graph is a function or procedure, and edges represent calls. So here we have a call graph, and these edges are labeled with some, let's say, profiling information where we annotate, how many times each function call is being invoked. So you'll notice that in this case we have 2 edges going from C to E. Why is that? What? Yeah, because basically C calls E in 2 different places. So we can either represent those separately as 2 edges, or we can also just put them all together into one edge. There's a choice there of how you represent things. And here, this loop here represents basically recursion.
What would that mean if it was the same line?
What?
If it was the same line, how would that help you? Meaning, like, if I called E from C in 100 different lines, like with other stuff in between, wouldn't it make more sense? Like, I wouldn't want to inline 100 of them necessarily. But
Wait.
you said where the C goes to E 100 and the 5.
Yeah.
So you can put them together if you want. What scenario would I want to?
Well, the 100 represents is like profiling information. It tells you that that's being run
Right.
that call is being run 100 times. So why would I want to represent these together?
Yes.
If I don't care about distinguishing, I mean, we'll see that when we do interprocedural analysis, I mean, we don't always need that information. We may want to know who calls E. Well, in this case, B and C, you don't need to have multiple edges.
So for a case where you're not inlining.
Yeah, I mean, there are cases where you just don't care about the particular call sites, but yeah.
Okay.
So, I mean, building a call graph is not easy. It turns out that there's a whole other, I mean, it turns out that building a call graph can be very, very hard. The reason why it's hard is because you have indirect calls, so calls through function pointers and calls through, virtual methods, and when you do that, you don't know where it's going to go. And it turns out that function pointers are used a lot. Okay, it's a very, very common feature. So if you look at the Linux kernel, for example, if you try to build a call graph for the Linux kernel, there are tons and tons of callbacks, where basically you actually pass these callbacks, and you actually, when you do something, or when you're done, call me back. So you kind of register, you can have a whole bunch of arrays of function pointers essentially. And in actually the Linux kernel, they also store function pointers inside of structures, and they actually using that they simulate a kind of OO programming. Right, so basically what they do is that they have the data in the structure, and then when you want to call an operation on it, there's actually a function pointer inside of that structure that tells you how to do that operation. So it turns out that you actually have in practice a lot of function pointers, which create a big mess for creating these call graphs. But okay, I mean, the point is, let's say that somehow you actually got your call graph. The other question is, where are you going to perform inlining? Where in the compiler are you going to do inlining? So there's many choices.
Before the other optimization process?
What?
Before the other optimization process, because then you can optimize the inline.
Yeah, so that's absolutely. So that totally makes sense. It's like you should inline before you run all the other optimization passes, because you want to inline and then do the rest. Clean up after yourself. But what about separate compilation? So when you compile, for example, a C file, a lot of times you're only seeing that C file. So how do you now do inlining? Right? I mean, basically you're saying do at the very beginning. Well, okay, so in a C compiler, I'm seeing my one file at a time. I have a file, I'm seeing it there. How do I inline? Because I'm not seeing the rest of the program. So in some sense, right, it's like you're saying let's do it really early, but the problem is at this point you're not seeing all the functions that are available for inlining. And that's why, coincidentally, in C++ you have all these header files that include code, because if you want to inline something, it mostly has to be in the header file. So when you include the header file, the compiler sees it. Something that's not in a header file, it's very hard to do inlining across different files in C++, for example. Now, of course, you can do inlining very late as well. So, I mean, at some level, you may have to wait all the way until you do linking. And some actually, there are inliners that work when you get to the linking stage. That's where you see everything. At that point, you have information about everything. You see all the functions. You really see all the calls between different things. But unfortunately, at that point, it's really late and you can't do post-processing optimizations after you've actually been on. So it turns out that when the compiler inline is actually another big issue. It's complicated. People do it at all different levels. There's been research that shows that there's benefits and trade-offs at every single stage you could possibly do. In fact, you can even do inline at runtime, right? Like in a JIT compiler where you actually literally see the things that are happening and you decide which things to inline because you realize they're hot and therefore you need to inline them. I mean, we actually saw some of these kind of systems at the beginning when we read papers on the JIT compilers. So, okay. So let's say you decide to do inlining. What are the pros and cons? Is inlining always a good thing? Can it be a bad thing? What's the
pros? You get all the other analysis and optimization that you
So
don't
pros,
get procedural.
right? Pros, you basically get the benefit of essentially you get the benefit of doing inner procedural without really doing inner procedural because it's all right. And you also get rid of the call overhead, the actual jump, setting up all the stack and all that stuff. Okay, this sounds really good. So it sounds like we should just be doing this all the time. Code bloat. Okay, so if we do too much inlining, then we get code bloat, and that can affect performance in terms of the instruction cache. But it also can cause problems for you in your analysis if all of a sudden your control flow graph, instead of being a relatively small thing, you kind of inlining it becomes huge, then your analysis that runs on this one procedure at a time may get harder and harder to run. So, okay, code bloat. Is there anything else?
How would the compiler decide whether or not it's a good idea? I'm thinking of like a for loop that's going to run multiple hundreds of times and it's calling a function in it. Like, does it unfold the loop? Or does it try to inline it and leave the loop? Or...
Right, so part of the problem with inlining is that you want to determine how much code bloat you're going to get.
Right.
But the problem is, once you do inlining, it may look like you're inlining something that's really large. But once you do optimizations on that, within the context of where it's inline, it may actually shrink. So for example, you may have a function that basically says if flag, and on one side it does one thing, on the other side it does 10 million things. And it turns out that most of the time you call it with the flag being true. So most of the time it's actually a really tiny little thing. But in the rare case, it's this large, so most call cycles call it with true. And just a few cases you'll call it false. So basically every time you call it true, it's kind of beneficial for inlining because if you inline it, you then optimize it, it'll kind of totally shrink. So in some sense, inlining, when you make an inlining decision, you have to kind of predict in some ways what's going to happen post-optimization, which is actually why inlining decisions can be hard. Now, the simplest way to do inlining is to give yourself a budget, say I don't want to increase the code bloat by more than 10%, and then start looking at the most frequently called sites, the smallest function, and inline things like that. That's what most compilers will do. And they'll have heuristics for seeing, sometimes actually inlining doesn't cause any code bloat because it's a one-line instruction. Inlining it is literally just going to be the same size as doing the call. So in some cases it's just a no-brainer. But when it gets to more complicated things, usually people use very simple heuristics, but there have been a lot of work on doing way more complicated things. So recursion can also be kind of weird because, when you inline a function that calls itself, it's really weird.
What is nested calls, right?
What?
Or nested calls, like a function that calls a function even if it's not the same one.
Yeah, well, those are not that bad. They'll just kind of remain there.
You have to decide which one's better.
Right.
Maybe it's only called in one spot, but the parent is called all over the place if you inlined it.
Right.
You like it.
So you can also do this thing called virtual inlining, which is to simulate inline during analysis and then see if you want to perform it or not. But that's expensive, right? So Now, we've already talked a little bit about this, right? So there's the saw. Okay, so we have caller and callee. So let me just make sure that we all are on the same page. Caller is the person is the thing doing the calling, and the callee is the thing being called. So caller calls callee. like employer and employee. So caller, callee, so basically the size of these things matters, the frequency, the benefits you get from optimization later on, and maybe even, so now compilers allow you to kind of say inline, these inline things, but in most cases they kind of ignore those heuristics. But now they have other heuristics that say, no, really, I really need you to inline it. It's like the underscore inline. If you put that, then it really inlines it. Okay. There's many ways to do it. I'm actually gonna kind of skip all of this. And the only thing I want to mention is that there are actually machine learning techniques that people use to actually predict whether it's a good idea to inline or not. They've also used machine learning to basically figure out how much to unroll a loop. So you have another optimization where it's really dependent on, you have to fine tune it. It's loop unrolling. So that's when you have a loop that has a small number of instructions, and you kind of unroll it a certain number of times to get more flexibility with your scheduling. Turns out it's actually kind of complicated to figure out exactly when to inline, when to do these kind of unrollings and by what factor. And people have looked at machine learning techniques for doing this. It's kind of cool. If you want to read the paper, I can point you to this. Yeah.
Sorry, and why sometimes it's a bad idea?
To do what?
Why sometimes it's a bad idea to inline? Why is it?
So, inlining leads to code bloat. And code bloat leads to pressure on the instruction cache of your it just leads to memory pressure, and in particular on your instruction cache. So, so that's an example where right, so as an example, if you have a loop, a tight loop, and in that loop, okay, here's an example. You have a loop, and in that loop you call a function f twice. So you call f once and you call it again. That's the only thing this loop does. And inside of f, the size of f, the number of instructions of f, is exactly the amount that fits in your instruction cache. Minus a few things, so you allow yourself to put the actual loop as well in the instruction cache, but it mostly fits. So then, if you have this thing where you have this loop, you call f once, you call f again, now everything, this entire loop and this entire function can now all fit in your instruction cache. Okay? And let's say this is a kernel of a computation, so you're going to get this you're going to get this instruction cache benefit. Now let's suppose you inline both calls to f. Now you're going to have the body replicated twice for f, and let's assume that because you were basically on the verge, your f was just on the verge of fitting in the instruction cache. Now with two bodies of f inside of your loop, right? The loop now has two bodies of f. It doesn't fit in your instruction cache anymore, right? So now your main loop inside of your core loop inside of your computation doesn't fit in the instruction cache, and you get a lot more cache misses.
Okay, but so what about, for example, if you've got some library code and it's sitting in like different page in memory unless you like inline that function?
What's that? So if you have a library that fits in another piece of memory.
Yeah, and instead of making a call to that library, you like inline that piece of code.
Right, but the issue is this, right? The issue is you have five. So the problem is if you have only one call to that thing, sure, you should inline it. But the problem is when you have a function, a lot of times you have multiple calls in your program to that function. So now which ones do you inline? If you inline all of them, then you're going to get this replication of code that's going to basically put a lot more pressure on your instruction cache. Because now you're going to have the same code replicated in many different places, and the architecture will not be able to notice that it's the same instructions. So it'll just put a lot more pressure on your iCache.
Okay, sure. And there's like a heuristic how you make the decision, right?
Yeah, a lot of it are heuristics. It's very hard to figure out exactly what the right decision is to make. And it's also, it's also architecture dependent. It depends on a lot of these. So you can actually do modeling to try to figure out, is it on, it turns out it's really hard.
Does it go the other way? For example, is it like the replicated sections of code find inside that it's going to create?
Yeah, so actually it turns out that there are some
Outlining.
Yeah, outlining. So actually, there was, but actually, see, this is what happens when you have benchmarks, because there was like some benchmarks that actually had manually optimized code. So sometimes people, because the compilers don't listen to programmers anymore, sometimes when people really care about performance, like, okay, this is my computational kernel, I really want to make sure they kind of inline things by themselves. And so it turns out that there was this benchmark. So I heard this story from this guru compiler guy who used to work at Sun in their compiler group and then was at Microsoft in the compiler group. And they had these benchmarks that had been hand optimized in this way. So now you had all these kind of replicated code, and then there was this compiler that actually had this specially designed optimization that would do exactly basically, yeah. Because on some architectures, it would not make sense to actually have it be inline. Because on some architectures, you're constrained on ICAPS, it's actually better to put them all together. And so it would do this outlining. But it was very specialized to a particular case. And the thing is, at the end of the day, it's not clear whether it's a win or not. It's a very complicated optimization to do. And then it's like, is it a win? I don't know. Now, of course, with all these things, what you can do is you can try them out. Right? So you can imagine now that you have on Amazon, you have like tons of like clusters of computers, so you can imagine doing this thing where it's like, well, you know what, I really want let me try it out. Let me try out this and that, all this stuff. The problem is that it's very, very expensive. It's combinatorially expensive, right? Your inlining decision is basically every function you can decide to inline versus not. So at the end of the day, you have this combinatorial explosion of how many programs you have to decide, you have to kind of evaluate. That's why machine learning, when you have a huge space like that, machine learning can kind of sometimes make headway on those things. Okay, does that make sense? So what should we do now? We have two options. We can keep on doing this, or we can talk about the paper, the pointer analysis paper. Do you guys want to talk about the pointer analysis paper? Let's talk a little bit about the pointer analysis paper. What do people get out of that paper? So that paper was actually that gave you a flavor if you read that, what people deal with when they actually do Anderson, right? So Anderson, when we saw on the screen here, it was actually a very simple kind of like, okay, you have this graph, you add these things. But in reality, it turns out that getting those things to run efficiently is actually non-trivial. So what did people get out of that paper? What's kind of the things that struck you?
I found it funny that nobody tried it before.
Nobody tried what?
Well, the one being that, you can do this statically off, like before you.
You mean the cycle elimination?
Yeah.
So okay, so one of the things that
other people try it,
right.
But you can do it offline.
So one key thing is that it turns out you get cycles, which are basically they're all equivalences. And so, because they're basically constraints of this form like A subset of B, which is a subset of C, which is a subset of A. So really what that means is they all need to be equal. And you can collapse those into one node, which makes the graph much smaller, and then you can propagate your points to sets much more quickly. And so they had a whole bunch of things which is offline and online and all these different things. And of course, it wasn't just offline. The problem is offline is not, the reason why I couldn't do it is because offline is hard. Because when you do things offline, the problem with points to analysis is that you get these complicated instructions like star x gets something. When you have a star x, right, the actual constraints you have to propagate depend on the points to set of x. So you may not know until runtime what exactly is going to be in your cycle. So that's why they have to do this kind of pre-thing, and then they kind of do some amount of things. So they have to kind of be clever about it. It's not like you just do things offline. It's offline and online, so it's this hybrid approach. Okay, what else? Come on. What else did you get out of it? Who else? Did you guys read the paper? You read enough of it to write down the 3 insights that you have to do, and then you can read it.
They also said,
Like, what? Yeah, go ahead, no, yeah.
They also had the concept that we don't actually have to detect the cycle. If we witness the outcome of what we are going to do is present, then we can just treat it as a cycle,
Okay,
which was convenient.
right, okay, so what else? Yeah,
Well, they said Anderson is pretty doable for them, and I thought we read in the class that Anderson is not doable.
well, they are, so Anderson is pretty doable, but they're not, they're only looking at like, 2 million lines of code at this point. So if you look at larger things like the Linux kernel, it turns out it's not easy. Now, the other thing is that you have to do these clever things, right? You can't just like run a vanilla version of Anderson. You really have to do these fancy optimizations to basically get it to run on these larger benchmarks. Yeah.
I didn't get what they meant by two parts of their high group detection. And so it's like one of them is offline. I didn't get it.
So basically what they're trying to do is they're trying to detect cycles. So what they do is that, basically the way they do it is that you create this graph that represents the constraints, the points to constraints. Basically, based on every statement that you see, they were creating these kind of subset constraints. And what happens is, once you're done with that graph, you then have to start propagating things across this graph. So for example, if they have something like this, then basically anything that if A points to something, then, sorry, it's the other way around actually. If A is a subset of B, sorry, yeah, exactly. So if A points to something, then B needs to point to that same thing, right? So basically you have to add, anything that A points to, you have to now go and add it to B, right, in terms of points to set. So what they do is they build all this graph with all these constraints set up, and that's the basic thing. And then what they do is they have to compute this transitive, what they call the transitive closure. And that's where they start propagating these points to sets. What they're trying to do is that, so the cycles, the point is that cycles may actually only appear once you actually start propagating things in the points to graph. And what they're trying to do is they're trying to eliminate the cycles ahead of time. And they can't do it fully. They can do it in some cases, and in some cases they have to kind of leave some amount of checking until they actually know, they kind of see what certain things point to. So it's something they try to do, you can think of it as the general concept of this idea of staging, was that you try to do as much as you can at the earlier phase, and then leave some residual work to be done when you actually get to the online phase.
So what is the difference between offline and online? Does it mean that you instrument the code and do the online part? What does it mean exactly by online?
So online means, so basically the way that they're setting up their analysis, that they set up a constraint graph. And once they set up the constraint graph, then they kind of propagate points to sets through that constraint graph. Online means that they do the cycle detection while they're doing this propagation of the constraint, of the point to inside of this graph. Whereas offline means that you build the constraint graph, and before you even run this transitive closure algorithm, at that point, you try to do cycle detection. And then, once you're done with cycle detection, then you try to do your constraint propagation, the point to set propagation. So it doesn't have to do with running it at runtime versus not. All of this is static analysis. Yeah. So, okay, the other thing that you guys may have noticed is they talk about representing these sets. So they talk about two representations, sparse bit vectors and BDDs, binary distributed diagrams. So the intuition is that, all of these things are sets, right? So each point to set is you have a variable and it points to a whole bunch of things. And so you can encode, if you number things, you can basically encode them as a bit vector, right? So the bit vector represents, every bit represents whether that thing is set or not. And there's sparse bit vector implementations that actually allow you to, if you have lots of zeros in your bit vectors, you only represent the parts that have actually have data. So you basically you can imagine you can store kind of a linked list of things that, dense regions or things, or a linked list of all the words that actually have things in them. And if you don't find it in that linked list, then it's just not there. It's just going to be zero. And they compare that to BDDs. BDDs are another representation of sets. So do people know what BDDs are? Binary decision diagrams. You guys have got those? Did you guys get it from the paper? Did everybody look it up online? Not in detail.
I imagine it's a binary tree. You just have to
So basically, a binary decision diagram is a tree, exactly. So it's a tree where you basically have you have layers in the tree, and at every layer you basically have a particular variable. So let's say here you have another variable called b, and what you do is this allows you to encode a function on A and B, where A and B are bits. Okay? So basically, the way you decide, so this function, if you have, let's say, A is 1 and B is 1, then basically what you can do is, if this represents 1 and this represents 0, then you just go 1, 1, and this, let's say we'll put the 0 value here, and we'll put the 1 value here, and we'll put, actually no. What's this? I'm going to put 0, 0. So what does this represent? This represents a function from two Boolean variables, A and B, that are both either 0, 1, and it outputs a bit, right? And what is this function here? It's n. Now, it turns out that you can actually represent, you could put many variables here, right? So this is just two variables, but you could put like 100 variables, and you can create a huge tree that actually will tell you, if you give it these 100 variables, what the final bit will be. Will it be 1 or 0? And it turns out that the reason why, once you actually build these really large trees, you can actually compress them. So for example, here, I can just do this. Right? Right, because on this side, it's always going to be 0. So I don't need to, and in some ways, and then what you can do actually is you can basically have a 0 node and a 1 node, and then you basically have this, well, if you go on this side, you go here, and then you check for B, and if you go on this side, you get 1, otherwise if A is 0, then you go directly to 0. And it turns out this is an example where you can collapse the tree. When you actually reach for trees that have 100 or 200 variables, you can collapse the tree in many different ways. So you don't actually have to store the complete exponential massive tree. And it turns out that there's actually operations that allow you to take two BDDs and take the conjunction of them. So you take two functions on variables, and you can actually take the conjunction and the disjunction, and it basically allows you to build this representation for these different things. Yeah?
So these are not decision trees because they can be effective.
No, they are decision trees. They're binary decision diagrams. So BDDs are binary decision diagrams. So they are decision trees.
I mean, zero arrows going down.
What?
So we just always consider decisions going down. So second down.
Yeah, so there's no cycles in here. Oh, you mean,
If they're
this
unidirectional.
is not a cycle, this is just that it's a graph. It's just
So this should be directed, right?
yeah, it is directed, I should say, sure. It's a tree, so these are children. Okay. Okay, does that make sense? And so actually, how do you represent a bit vector using this thing? Well, basically, if you think about, let's say, having 100 variables, then basically, you can actually have those 100 variables, which are basically a bit vector of 100, mapped to either 0 or 1. Right? So if I have a function that takes, let me give it to you this way. If I have a function from 3 variables, a, b, and c, and it maps to either 0 or 1 for every binary value of a, and every binary value of b, and every binary value of c, what this function represents is it represents essentially a set. It represents, you can think of this as a bit vector, right? And it'll basically, this bit vector will be either true, will either map to 1 or to 0 for particular values. So if you map to, you can imagine this as mapping to 1 for a particular value of a bit pattern, and that's the bit pattern it represents. So anyway, that's a summary of BDDs. The point, the summary though was that BDDs were what? More efficient? In memory, but slower. Whereas bit vectors, exclusive bit vectors, or sparse bit vectors were faster, but took a lot more space. Okay. That's for the pointer stuff. Hand in your paper, and next time we'll continue with inlining.
So the next paper reading is for Tuesday?